Okay, sorry about that. I tried to switch over to a periodic table and lost track of my screen share. Okay, so we do have to go ahead and split up that lone pair in order to get all those chlorines to bond. So we've got phosphorus now with 5 groups surrounding it. So this is our 5-group example. Okay, so let's go ahead and go to the model. All right, so when 5 groups surrounds an atom, what we have is in the middle there, we have 3 in a plane, and then directly perpendicular to that, we have the 2 other atoms. So the bond angles are kind of funny here because we get 90 degrees between the plane and the top and bottom atoms, but then within the plane, we get 120 degrees. Okay, the name of this is trigonal bipyramidal. And obviously, if all of them are bonding regions, the molecular geometry is the same name. So we're going to go back to here, the 5-group example. The electron geometry is called trigonal bipyramidal. And that's because if you look at the structure, like kind of picture the top part. I can't draw on this for you. Picture the top part as a pyramid and the bottom part as a pyramid. Okay, bipyramidal. All right, the molecular geometry, also called trigonal bipyramidal. And the angles are 90 and 120. Okay, this is where, I should have pulled this up while I had my video changing. We're going to go ahead and pull up table 11.1. This always is kind of slow for me. All right, a little better than normal. Okay, so chapter 11 should be at the bottom here. It's probably in the next section. Yep. Tell you what, let's just do it this way. It'll go faster. Okay. There we go. Okay, so there is the complete table 11.1. You can find this in section 11.2. So we had those first halves on the top, the first half of the, in fact, I'm going to go ahead and take a quick screenshot so that I can kind of mark this up a bit. Go. All right, so we did 2, 3, and 4 groups, and now we're doing 5 groups. So the one we just did is all of them being bonds, and there's all these other examples of when we add lone pairs. So I think I have SF4 on there, but it's good to go through these because I don't have all of these different examples. All of these are in the simulation, and I think what I would do is go ahead and like write down the formula here, SF4, BF3, sorry, BRF3, and xenon difluoride. Okay, and maybe what I'll do is pull open the simulation and just show you these, but I think it's good practice for you to verify that these are the correct Lewis structures. Okay, so the names of how these change, these actually kind of, I'll show you how they look like it in the simulation, but as we add 1 lone pair, the molecular geometry is called seesaw. As we add 2, it's T-shaped. And then as we add 3, what happens is that it actually becomes linear because all of those lone pairs end up in that plane that are 120 degrees away from each other, but then the fluorine is up and down. So let's go over to that. So do I have every single one of these examples? I hope so. One thing that's interesting about trigonal bipyramidal, so here you can see the seesaw. Look, this is the seesaw. This is why it's called it. So one lone pair, 5 groups total, one of them being a lone pair, called seesaw. The angles, you still have that one that's used to be 120. It's squished down to 101. So that's actually a pretty dramatic decrease. And then you can see the 90s have been squished down to 88. Okay. The lone pair, when you add it in trigonal bipyramidal, it will always add to that plane that's in the middle. It will never add on the top or bottom. That's because, like we mentioned before, lone pairs kind of blob out. They take up a little bit more space than when they're attached to an atom in a bond. And so they need more room. So they will go to that area where they have 120 degrees separation between those other bonds, instead of being at the top or bottom where they would only have 90 degrees away from each other. I don't think they have all these other examples. Oh no, there's BF5. That's not the one I wanted. Was it? Oh, it was BRF3. If they don't have it, we will go ahead and just make it. Yep, let's go over to the model. So 2 lone pairs, we said, and 3 bonds. So this is called T-shaped. That shouldn't be that surprising. Okay, you've got the 2 lone pairs in the plane. So these would be the 3 that are in the plane, and then the 1 up and down. The angles actually stay at 90, all of them, because there isn't a bond angle in the plane, because those lone pairs don't make an angle. It's a bond angle. It's only between bonds. Now, in a real life, they would squish down a little bit, you know, maybe 88, 87. Okay, and then last one, 5 groups, 3 of which that are lone pair, and now you can see why it's linear. So all 3 of those lone pairs are in the plane, and then you've got the up and down ones. So this would be xenon difluoride, XeF2. This is our first time we've seen a noble gas bonding. Xenon actually really likes to bond. It's big, its electrons are nice and high in energy. That's why that happens. Okay, last thing, we're going to consider 6 groups. So I'm going to go ahead and do that since we're here. 4, 5, 6. Okay, this is called octahedral. Not because there are 8 things attached to it, there are 6. But if you were to put on sides between all 3 atoms that are like, I can't do it because I can't draw on it. If you were to put sides on, you'd basically have a 4-sided pyramid on top and a 4-sided pyramid on bottom, or 8 sides, which is why they call it octahedral. Okay, all of the bond angles are 90 degrees apart. So the example we have in the notes with this is SF6. So sulfur looks like this, and then we throw the fluorines in. And go ahead and pause if you haven't already. And then we add those bonds in. Only way to do it is to break up those pairs. Oh, I just realized I had the wrong number of electrons on here. 1, 2, 3, 4. No, I have 6. Oh, I do this all the time. I don't know why this keeps happening. I keep bonding an atom to a single electron. There we go. All right, so that's SF6. 6 bonds all surrounding that sulfur. Okay, since I don't have additional examples in here, I'm going to go ahead and show you in the simulation as well as in this table. So we did all of those examples, and now we're going to look at the others for 6 groups. where we have one lone pair, two lone pairs. Now, there are ones with additional lone pairs. They're a lot less common, and so we don't talk about their examples nearly as much, so that's why they're not included on this table. If you look in the notes at my table, I have the additional, if there are three bonds, three bonds, but 6 groups, 3 bonds, 3 lone pairs, that would be also called T-shaped, or 6 groups, 4 lone pairs, that would be called linear. Okay, so you're going to go through examples like this in the homework. Okay, so it's not like this is going to be the only thing you're going to review it. But let's go ahead back to the simulation. So we've got the 6 groups here. We substitute in a lone pair for one of those. Okay, this is called square pyramidal. The only thing you have to remember about actual bond angles versus true ones is that they get slightly less than whatever they were predicted. So with this one, the predicted bond angle is 90, but the actual bond angle is going to be slightly less. That's all you need to know, slightly less. Okay, replacing one more bond, still 6 groups, 2 of which are lone pairs now. So you can see why that's called square planar. Now, I erased one instead of added one. 3 lone pairs, 3 bonds, also called T-shaped. And finally, 4 lone pairs, 2 bonds, also called linear. So again, we're kind of finishing up here. I really want to emphasize the usefulness of the simulation, especially as you're beginning to learn this stuff. So once you hit next week and you're like doing practice exams and reviewing for the exam itself, you don't want to be using the simulation at that point. You want to have kind of exhausted it, pictured those molecules, and now be able to rely on just this table, which I'm going to tell you about in a second. Same thing with the table up here. Well, that's in the textbook, this one, but complete. Use that while you're studying, but don't use it by, let's say, Wednesday of next week, okay? Because you want to be preparing for the exam. You want to be really testing yourself that you know the material. So this is a little bit, it is very much not a complete table. This is a little bit of a cheat sheet to help you in remembering the different structures that we're going to see with all of these electron pair geometries and molecular shapes. Okay, so I do give you the names of the more complicated ones. I don't think it's that hard to memorize those, but I'm generous when it comes to memorizing. So know how to interpret this table. So for example, if I had, let's see, I think it was SF4. So SF4 looks like this. It's got a lone pair and then the 4 fluorines coming off of it. So it has a total of 5 groups. So I'm going to go to row 5. This is 1, 2, 3. Oh, that is messed up. 2, 3, 4, 5, and 6 groups. And then I'm going to look at the one that has 4 of them as bonds and 1 of them is a lone pair. So now I know that the name is Seesaw. Now, I don't give you the angles for these, right? You're going to need to know that the angle here between these two is 120, and then these are 90. So if I asked you the bond angles, the true bond angles, you would say they're less than 90 and less than 120. If you have options for just like less than 90, less than 120, let's say less than 109.5, less than 90 and less than 120, I don't know, 180, not less than 180, 180, maybe I give you another one that's like a combination, like 120 and 109.5. Okay, so this is the correct one. You want to select the one that has both of them because this is not complete. Okay, so you do need to know all of the other information that's not on this sheet. You're going to need to know how to interpret it. You're going to need to know these names: trigonal, planar, bent. You're going to need to know how to determine the electron geometry as well as the molecular geometry. So there's lots of information that's not given on here. It's just to guide you. So what I would say is by Wednesday, you want to be only using this table, obviously the version on the exam equation sheet that doesn't have all of these notes on it. Okay? All right. I pulled out molecular geometry when I did the notes. I decided not to do it that way when we did it in class. So we've actually already done all of these. Okay, so that's the end of today's material. Fridays is it's a little bit of a struggle for people. So we're going to talk about polar bonds again. And then we're also going to talk about what does that mean in a molecule, because the only polar bonds we've talked about are between two individual atoms. So what happens when you have an entire molecule where you've got bonds between two atoms, but you've got 5 of those bonds or 3 of those bonds or whatever? Okay, so that's what we're going on Friday. Please feel free to email me anytime today or tomorrow with questions about the lecture. I'm happy to respond to those.